Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Arteris with Ashley Stevens. We're going to talk today about the benefits and challenges of using chiplets. Ashley, as we move from SoCs to multi-chip packages, what sort of challenges are you starting to see?
Well, first of all, you see challenges of partitioning your design across multiple chiplets, bandwidths you need to interface the chiplets to each other, and then a real complexity is when you get into fully coherent chiplets. They are much more complex than non-coherent chiplets. Non-coherent is already widely used by many people in the industry, including our customers, but coherent adds a whole layer of complexity to the equation.
Let's take a closer look.
Sure.
Ashley, what are we looking at?
Okay, well here you see a traditional monolithic die. So in the past, normally SoCs were a single die. You built the whole thing on one chip. So here we have an example with a CPU, GPU, some memory, and peripherals. We're running into challenges with, for example, just the size of the die. As the designs get bigger and more complex, there's actually a limit, the reticle limit, which is 858 millimeters squared currently, and you simply can't go bigger than that. Additionally, when you do go big, even if you're not quite that big, the yields go down because the chances of there being a failure in the chip is much higher because it's bigger. Additionally, some aspects of the chip may need special technology. So for example, peripherals, they may have high voltage or they may have RF or various other types of interfaces. The memory doesn't need special technology, but it hasn't improved since about 7 nanometer and certainly not since 5 nanometer. And so there's really a wasted cost if you have a lot of memory because you're using this very expensive modern technology in 3 or 2 nanometer to build something that could be built just as easily in 7 or 5.
And this has been one of the big problems with SRAM, right? It's the so-called memory wall. It does not scale, and this is why people have to now go to multi-die types of implementations.
Yeah, it depends on the size of the memory. If you have a lot of memory, it's really a high cost to use that on a very advanced process. When you move to L3 cache, then you'll find that because it's so large, it's really not very cost effective to build it on a modern process. You may as well build it on an older process and save money as a chiplet.
But putting these systems together with chiplets is not exactly easy either, right?
It's certainly not simple. There's really two kinds of interfaces between chiplets. So already non-coherent interfaces are pretty common and our customers already do that. But when you get to coherent interfaces, it's much more complicated. So typically the non-coherent is used to interface just data from one place to another. So GPUs, for example, and accelerators, they will use non-coherent interfaces to just pump data from A to B, from one chiplet to another. But when you get to CPUs, you want to scale the number of CPUs over chiplets. If you want full cache coherency, as I said earlier, it just gets way more complicated.
And we tend to break things into CPUs and GPUs, but really there are bits and pieces of those that are very different too, right? So a CPU may be an accelerator as well. It's a processing element, and a GPU may be multiple GPUs that are doing some of the processing now for AI type of applications, with the CPUs now doing some of that as well, or doing the management functions.
Yeah, so as regards coherency, anytime you have caches that are sharing data, you're going to need coherency because otherwise you're going to have the wrong data. So actually, typically these days, your accelerator or GPU, most of the data will not be shared and can be non-coherent. But obviously there is some communication between CPU and GPU, and therefore that will need to be coherent. So you actually have need for both in most designs.
There are trade-offs here though too, right? Because distance, you basically, when you have it all on one chip, the distances that signals need to travel is much shorter. You can have very high bandwidth types of interconnects. As you move into a multi-chip type of implementation, that becomes a little further apart. You actually pay a price for that, right?
Well, that is true. The issues that you have are the usual two, if you like, which is latency and bandwidth. So you have increased latency of talking across an interface, and also you have a bandwidth limitation in terms of how much bandwidth you can get between devices. Of course, for example, there are standards like UCIe, which is becoming popular in the industry. You can gang them up. So typically, people might use just one UCI interface, but there's no reason why you can't have more. So you could have, for example, 2 or 4 UCI interfaces to increase that bandwidth.
One of the advantages of moving to an advanced package is that you don't necessarily need exactly the same type of device. You can have heterogeneous types of dies too, right?
Yeah, so there's kind of two kind of philosophies, which is homogeneous, where you design one die and you replicate it multiple times, and so maybe 2 or 4 times, and that allows you to scale performance according to your requirements. And then there's heterogeneous, for example, in this example, where you have different functions on different chips, and this allows you to mix and match the designs. One big benefit of this is that something like a CPU or GPU is extremely expensive to develop with huge design teams. But things, for example, the peripheral chip is potentially much quicker and easier to design, and also it can work on a different design cadence. So this might take 2 or 3 years to develop, where a peripheral chip might take only 1 year. So that means you can do different peripheral chips, and therefore you can do different customizations or different variations of the overall solution according to market segment.
This has long been the argument for chiplets. It just took a very long time to get here. Think about analog, for example. Why not develop it in whatever process it makes sense? It does not benefit from scaling, only digital logic does. So now what you're doing is saying, okay, we can put in exactly what we need to based upon cost, based upon performance, based upon whatever workload we're trying to process here, right?
Yeah, I mean, it used to be in the early days, not so long ago, that the cost of a wafer was basically the same in terms of per millimeter squared. You got more transistors on a smaller geometry, but the overall wafer was the same. Well, that is not true today. The cost of wafers has gone up exponentially on modern processes. So that means it's very wasteful to be developing something like analog that you mentioned on a modern process. And we also mentioned memory, where again, it doesn't scale beyond 5 or 7 nanometers. So it's very wasteful if you have a lot of memory to use a very modern process.
But now what you have to figure out as you're developing these is, what is your workload going to be? How are you going to utilize this? So do I need more than one CPU? Do I need more than one GPU, right?
Yeah, so you have to partition your design across your chiplets. I think typically most people today are designing individual chiplets as almost like separate projects, and they put them together. They verify them together in an environment, and they build the whole thing. But I think in the future, things are going to get more advanced, and people are going to move to a methodology where you design the whole thing as one very large design, and then you can look at how you partition that into multiple chiplets, and that's where a Magellan software can come in to help you.
You bring up a good point, which is partitioning and just how important it is in some of these designs. What sort of problems do engineers typically run into, and how do you solve them?
Well, today, I think that architects will specify their design according to what they think is a good partitioning. That's actually quite difficult, and it's certainly hard to optimize. So in the future, I see that people will move to a methodology where they design the whole thing, and then they can look at how they cut it up, what's the optimal partitioning for that design, and it might not be what you first think of.
You also can partition by domain and also by workload too, right? They may vary very much even within the same domain.
Yeah, I mean, I think the typical approach for engineers coming at it is to partition by domain, but that might not be the optimal solution. So going forward, I see the process to be that you design the whole system and you look at how you optimize the partitioning, you look at the data flows within the system, and then you figure out which is the most optimal partitioning for your solution. So you also need to look at, as we mentioned earlier, latency and bandwidth, and which are the data movements that are most appropriate to the slightly higher latency and slightly lower bandwidth you're going to get across a chiplet.
So if you take what you're talking about here up a level of abstraction, really what you're doing is adding granularity into things that you'd never had a view into before, right? And you can make these little changes that you never could in the past.
Yeah, I mean, one of the sort of benefits is that, as I said, designing this whole chip as one is very, very expensive. These large chips can cost $300 million or more to develop. With this approach, you can design these individual chiplets, these CPUs and GPUs will be very expensive, but then you can look at how you can, for example, create different sized memory chiplets, different peripheral chiplets, according to the requirements of the market.
So your upfront costs can be fairly significant, but at the same time, your derivatives may be much less costly too, right?
Yeah, that's absolutely right. To design, these four chiplets, and also the interposer that you need to connect them together. So, by the way, an interposer is like a tiny PCB that we used to know from traditional design, except instead of making it out of other sort of resin technology, it's made out of actually silicon. So, it's like a silicon chip that only the wires and not the transistors. And the silicon interposer is used to connect together the individual chiplets. So, these things here are the individual chiplets, and then it is your connection topology. Now, agreed, to make this whole solution is going to cost you a bit more than this, but you have much more flexibility in terms of how you develop it. So you can build a system with different sizes of memories or different peripheral blocks according to what you need in the design, and these are much quicker and cheaper to redesign than this whole thing. So you can spin the designs much more quickly according to your requirements as they change.
So you may get 80% of your design done and say, okay, here's the 20% we can continue to play with as we go forward, but the other 80% we know it works.
Yeah, that's right. You have this working 80%, the expensive part of the CPU and GPU to develop, and then you can quickly iterate designs according to the requirements. As you say, that 80% of the work is expensive to do, but then you have a much cheaper iteration. So if you're going to do multiple iterations, it's going to be much cheaper overall in the long term.
Where are you seeing multi-die systems being deployed today?
Today, most of the multi-die solutions are being developed by large manufacturers of CPUs. You know who they are. They're designing the whole thing in-house, and they're doing it in order to reduce cost and to increase performance. Going forward, we expect this approach to proliferate more throughout the industry as it matures and develops. And so we see this moving into, first of all, data centers, and then another a market which is very interested in this is automotive, and there's a lot of activity in automotive. They move somewhat slow, automotive, but they're already starting on their journey.
Well, in automotive also, they're looking at this as a way of adding features by chiplet too, right?
Yeah, one of the things about automotive is that they have come from a background of having individual modules, individual ECUs that they put in their car according to different requirements. So they can have a common ECU for a low-end car, and they can add on additional ECUs for the more premium market cars. So moving to what we call as a software-defined vehicle, that is something that's being adopted by some of the more leading-edge automotive manufacturers and new entrants. But for some of the existing players, the idea of using chiplets is very attractive because it follows the same kind of model that they are used to, with adding hardware features with different pieces of hardware technology. But in this case, instead of using little blocks of plastic with some chips inside, they're actually putting it into one chiplet-based system.
Ashley Stevens, thanks for a great explanation.
Thank you.